It is my pleasure to introduce Dr. Lei Wu, who is the Principal Data Scientist and Manager at Ancestry.com. He now drives data science team in San Francisco, Provo, Utah, and China. Lei's team is building machine learning and AI capability in Ancestry. Lei, thank you.
Yeah, thank you for the introduction. Hello, everyone. I'm Lei Wu from Ancestry Data Science. Today, I'm very glad to be here and share some of the recent work at Ancestry Data Science to build a big tree. We're actually using machine learning to generate a big tree that is a knowledge graph about humankind. So before I go into the detail about what is big tree and how we build this big tree, I want to ask one very important question, and I want answer from you. Which of the following do you think is most important to you? Friends, jobs, or your family? Family. Okay, I got all the answers is family. So I will tell you that what Facebook is doing is they build a network to help you manage and discover your friendship. And what LinkedIn is doing is they are building a big network to help you manage your jobs, manage your talent. And what Ancestry is doing, we are building a big tree, is actually a huge network about your family members. So Ancestry is a global leader in the family history and consumer genomics. So you can use, I think some of you may have already used Ancestry.com, especially some senior people. They used to use Ancestry.com a lot to build their family trees. They want to discover who is in their family tree, where they come from, and who are connected to whom. So here is how Ancestry started. We started, I think it's 33 years ago, by starting to collecting some paper documents about family histories. Those paper documents used to be thrown into the trash bin if there's no Ancestry. We bought them. We invested around 200 million investments just to collecting all those documents, which should be thrown into the trash bin. And then we start to scan all those paper documents into digitized format. And then on top of that, we built the first search engine, which enabled us to search all the useful information from those paper documents, which is called Ancestry Search. And right now, today's Ancestry, we have more advanced tools, more and more content added into our database. And on top of that, we built machine intelligence. We built hint system. The hint system is actually a recommendation engine. Based on your interaction, your information, we can automatically detect who you might be interested in and recommend to you. And also, we built a big tree infrastructure I'm going to talk about today. Is more like a social network about all your family members, and how we discover them, and how we connect all the family trees together. And based on big tree, we can do social sharing and collaborations, make our users enabled to collaborate with other users and share their information. The main purpose for this system is we can connect different types of information together. And also, we can connect our users together to help each other discover their family history and know their family stories. 3 years ago, we launched a new product called Ancestry DNA. So basically, the idea is if you can spend only $99 to do a DNA test, then we can use your DNA to match our DNA database. So right now, Ancestry has the world's largest consumer DNA database. From those match, we can tell where you come from. We also can tell who is your relatives and what kind of relationship you have with those people. There are a lot of people, they use DNA to find their long-lost families. We have a TV series about that, how people find their family members through our DNA product. So here is the data science team. The main role for the data science team here is to use some advanced machine learning technologies like deep learning, natural language processing to transform those paper documents into digitized documents. We do form recognition. We know that what type of form are there. So we have around 200 different types of forms. And based on that, we know that where the location is and what information in that location represents. Is that name? Is that date of birth? Is that your residence address? Or maybe your spouse name or your kid's name? And also, we do handwritten recognition so that we can recognize all those handwritten records into digitized information we can index and search. Using advanced machine learning to enhance the natural language processing, we are able to correct some of the typos. Even there are some typo in the record, we can correct them. And we can detect most important events from those records and put that into your family tree. And also, we optimize for the search engine so that our ranking algorithm is more advanced. They can always find the most important information for you, most relevant and diverse. And on top of that, we have a recommendation engine. The recommendation engine basically will interact with the user. Once you sign up with Ancestry.com, you start to build your first family tree. And once you do that, every node you add to your family tree, the system will respond to that. So if you input a new name or you change a name in your family tree, then the system knows that some data changes. This feedback will feedback to our learning system. The learning system will immediately identify that there's some change there. They have to modify the model to customize a model for you to identify who you are most interested in. Then based on that, we can generate a ranking of all the information we gathered from the database, and then we can feed back to the user. Here is someone in other records might be related to your family. Do you want to add to your family tree? Here are some photos. We identify some people in the photo. They take a family photo with you. Maybe he is related to your family. Or we find someone who has shared a lot of similar DNA with you. Do you think he is one of your family members? Okay, let's take a short break to do some quiz to understand what data we have and why we built a big tree. The first question is, how many family trees do you think we have in Ancestry? The A is 80,000, B is 80 billion, C is 80 million, and D is 80 trillion. Make a guess. C? How do you know that? I will see, yeah. Okay, so you're good at test. Okay, so the other question is, how many family history records does Ancestry have? A is 18,000, B is 18 million, C is 18 billion, and D is 18 trillion. C? Yes, C again. Yeah, we have 18 billion family history records that we spent over like 20 years to collect. And how many individual profiles does Ancestry have? The individual profile, we mean the profile in our family trees. 8,000, B is 8 million, C is 8 billion, and D is 8 trillion. Yes, C again. Yeah, we have 8 billion individual profiles in our family trees. We want to stitch them, detect all the duplicates, and we want to stitch all the duplicate records together so that we can connect all the family trees into a very huge network. And finally is how many family photos and scanned documents does Ancestry have? A is 300,000, B is 300 million, C is 300 billion, and D is 300 trillion. D? B? Yes, that's B. Great change. Yes, we have 300 million family photos and scanned documents. Through that, we can do face recognition. We can identify who is in your family photo and how they connected to. We can generate hints from that to recommend more people to your family trees. Okay, so here comes the big tree. So since we have so many data, and we find that those data is super important especially to our users, how about we can connect them together to form a big network? So those data, I think, is more than Facebook, more than LinkedIn. And what if we connect them into a huge network? What will happen? Right? That's the motivation why we start to build the big tree. So actually, we generate some machine learning algorithm that can identify who is who. We can identify these two people, they are the same people, or these two people, they are different people, so that we can connect all the same people together to form a knowledge graph about all the people in our database. Based on this platform, we can easily know that from A to B, how they are connected, and what's the relationship between two people that seems have no relationship, and how do we find their useful information, stories about the family, how the family evolves over the time. So here is how we generate a big tree. First of all, we will merge all our database together. On top of that, we will do some feature extraction. The feature extraction will find the most important features to represent each of the records. And then we designed a very fast and efficient blocking algorithm. The blocking algorithm will tell us, like, these people are similar to each other. Which people should be the same? With high probability, these people are the same. And they actually blocking all our data into different bins. And in each of the bins, because we have so many data, we cannot just do one-one comparison. We have to block the data into small bins. And in each of the small bins, we have a personal compare engine. This engine will compare like how likely these two people are the same people. Then they will send the results to a stitch engine. The stitch engine actually takes the results from the compare engine, and then they start to stitch. Say, okay, these two people are the same, we should stitch them together. There might be some inconsistency of their records, but how do we merge them? That's the aggregator, right? If we have 10 records about the same people, we aggregate these 10 records together to generate a profile for that person. This profile will contain the name, date of birth, date of place, where they residence, how they change their residence, where they work, all of the information, their family member information together. We call it a profile. And finally is the evaluator. The evaluator will tell us how good each of the module is doing, like compare engine, how good is the stitch, how good is aggregate, and the quality of the profile. And all this infrastructure and database will be used for various products in Ancestry. So today I'm just focused on the compare engine because that is a core, and that is all the performance comes from the compare engine. The compare engine do a very simple task. It just compare two people and tell us how likely these two people are the same or not. Suppose here we have the first record is J. Black. Date of birth is March 1st, 1974. And the other record is Julia Black. We have his marriage date. We have spouse name. And we want to tell that whether these two records is about the same person or not. This seems a very simple task, but actually it's very complicated. Even for humans, we have a lot of experts in Ancestry. We call them professional genealogists. They are doing a lot of research to identify the ID of the person, whether they are the same or not. Even for them, sometimes compare two people, to compare two records is not an easy job. Let me give you an example here. I'm not sure whether you can see clearly because there's too many information on the screen. The name is Rebecca. The left is the first person A, the right is person B. The person A's name is Rebecca Horton, and person B is also Rebecca Horton. Both are female. One is born in 1713, and one is born in 1733, 34. They have the same father, they have same mother, they have very similar siblings. Do you think these two persons are the same person or not? Yes? Actually, they are different. After we do some research, we find that these two persons are two different persons, but why they have the same name, same father, same mother, and same sibling? That is because in that region, they have a culture. When one of their brothers died, they have to change their name as their brother's name. That's some local culture there. So yeah, after we realized they lived in that region, then we realized that they are actually using his sister's name as her name. They are actually their siblings. They are not the same person. Okay, let me give you another example here. Person one called Lanson Neil Singletary. Person two is called Vancing Singletary. Both are male. One is born in 1912. One is born in 1913. They have the same mother. They have, I think, one sibling overlap. Do you think they are the same person or different person? Same? Different? Yeah, I heard different voices here. Yeah, actually they are the same person. So why they have different name? It's because there's some record typo here. It should be Lansing instead of Vancing. In the record, it writes Lansing, but in the database, when they input into the database, you input as Vancing. But actually, they are the same people. So as I showed here, just two very simple examples, and we can tell that even for humans, it's very difficult for us to tell whether they are same or not. But the most difficult thing is we have 18 billion records like this. It's very hard even for human to manually compare who is who, right? So we have to use some machine algorithm to determine whether they are the same or not. This is extremely hard for machine to do that. And we have to design a good algorithm on that. So now I'm going to talk about how we evolve our algorithm. The first version of the compare engine is just some very simple rules, like whether the name match, whether date of birth match, whether the response name match. If they are all the same, we say same. If they are different, then we say different. This is very simple logic. But the only thing is we cannot handle very complicated cases, like those age cases I showed you. They completely fail the rule system. So the next thing we do is we improve our rule system based on some scores. If any of the field match, we add a score. If any of the field doesn't match, we subtract from the score. And finally, we return a score that is the probability, how likely whether these two people are the same people or not. But the problem is, how much score should we give if their name match or their date of birth match? Which is more important, or we can consider them equally. So it's very hard for a human to judge how much scores we need to give to each of the match. So here comes the ThunderCompare Engine. The ThunderCompare Engine is a machine learning engine that tells us which feature is more important and how much score we should give for each of the match. But this is not the end of the story. We have machine learning, but we realized that the machine learning may not work here because we have the garbage data. We have so many noise in the data, and we call it garbage in, garbage out. Right? If you directly put all those record data into a machine learning model, the machine learning model is not accurate at all because there are so many typos, so many errors, so many missing values there. To overcome that difficulty, so we designed some engine called ThunderCompare Engine V2. So in V2, the engine is more intelligent. It can automatically detect the data noise. Automatically tell us that what we should do with the data. We should clean, or we should recycle, or we should discard. By clean, we mean we estimate the missing values. We correct the typos there. Recycle means we have multiple different machine learning models, and these models share results and share data with each other. And discard means this information is purely noise. We should not use that. Otherwise, we will decrease the precision of our model. And also, we involved human intelligence here. We hired a lot of professional genealogists. They will give some feedback to some edge cases so that the machine learning model can be improved by incorporating the human intelligence here. Here's a more detail of the data flow, how the data goes. The green part is all the labels we collected, and the blue part is on the unlabeled data. So this is a semi-supervised active learning framework. So all the data goes through the pre-processing sampling pipeline. Then we do edge detection, whether it's easy case or edge case. Then we can train several different kind of machine learning models. These models will give us some compare scores. And all the unlabeled data will go through the compare engine again. And then based on their confidence score, we choose to accept their compare score, or we send to some auto-labelers. So we have 3 different auto-labelers. This is another machine learning model that tell us whether they should be same or different. If 3 of them agree with each other, then we say, okay, probably they are the same. If they don't agree with each other, we have to involve human intelligence here. So we have some progen to give us labels. So these labels will be put back into our training pipeline to improve our model. So this is an iterative process. After several iterations, the data is cleaned up and the model performance has been improved. So here is a comparison between the machine learning engine with a rule system. So we find the green bar is a machine learning engine. This is the quality, like accuracy of the compare. And the orange bar is a rule system. So we find by introducing the machine learning, the active learning framework, the data quality, the compare quality has been improved by 25.8%. And the compare speed has been increased by 130%. I think it's a great improvement by introducing machine learning and active learning framework. So here are some game-changing strategies for the big tree. By using machine learning, we construct a big tree. And using big tree, we can convert a big data into a big knowledge. The big data doesn't tell us anything unless we can convert that into a database, into a knowledge database. And we also engage our user into the modeling process. So anytime the user changes their family tree or do anything, they accept any of the hints into their family tree, those will be our feedback to the learning system. We married human intelligence with machine intelligence by involve the progen input to further improve our edge case detection and machine learning accuracy. So with big data, we know how people are connected to each other by connecting our database, connecting different family trees. And we can better understand our human relationship. And this system is real-time. As I mentioned, every change will be real-time responded by the machine system. And every user in our in Ancestry will have their own family story, will have their own recommendations. So it's a personalized system. So some takeaways. First of all, family history is important. As I think I got the answer from all of you that family is the most important thing, right? And also discover the family relationship between people is not an easy task. It's very difficult, it's very complicated, but very critical. We involved machine learning as a powerful tool to rebuild a knowledge graph about mankind so that we know that who is connected to who and how they are connected and how their family members and ancestors is doing and their family stories. And most important thing is we have the best data scientists to help us build this system. I think so far we have 18 data scientists working on related projects about big tree. And those data scientists, they are super smart. They come up with a lot of machine learning, new algorithms, new frameworks, and how to deal with this noisy, complicated data. This is very, very helpful, and it makes the project success in Ancestry. Finally, in data science, we believe, and I do believe that with big data, data science, machine learning, we can improve how we realize our family is, and we can better understand where we come from, and we can better understand what we are going to do for this family, for our families. Thank you.